And in particular, this paper, which is called End-to-End Referring Video Object Segmentation with Multimodal Transformers, the work done by Adam Botach and Chaim Baskin was the supervisor. You can see the link to the paper and to the GitHub in the bottom of the screen and also below the video. So I'll start from motivation and a bit overview of related work. I won't get into details. I assume that you know what is transformers, what are current trends in computer vision, what are tasks that we are solving, but I'll give a brief overview. And as for question, I can see the chat. If you have some questions, I'll check the chat once after every slide or something. And when I finish the slide, I'll check if there are some questions that I can answer. So the motivation, the overview, as I said, so instance segmentation is a well-known task. This is sample from RVOS dataset. In instance segmentation tasks, the goal is to provide a masks for the object in the image. In the scene that you can see here is some room and all the objects are segmented. So providing a mask per object usually requires less supervision than, let's say, classification, since each input provides much more input, much more signal for training, because each pixel either have a mask or doesn't have a mask, so we have more information per image. And one of the ways to solve this segmentation problem and detection, which is a simpler problem of finding bounding boxes, is the work called DETR. The main idea is to use transformers, and the way they use transformers significantly simplifies the pipeline of object detection. So they use regular CNN feature extractor, which extracts features per image as in regular object detection task or classification task. But instead of complicated region proposals and two-stage detection, the feature that just enter a transformer encoder decoder, which outputs a set of box prediction, which are then matched by bipartite laws to the ground truth bounding boxes. And the method is actually so simple that you can feed the whole code of the method in like single page or maybe single screen of code. And it works pretty well at the level of faster CNN, I think, or maybe even a bit better. Another related work, which takes us to a bit a different direction, is CLIP. And CLIP was groundbreaking work in a sense that it's managed to bring together textual encoding and image encoding. The way it did it, it used the contrastive loss to train a mutual latent space between the texts and the images. And this allows, for example, what's called zero-shot classification, when you define classifying labels by just inputting the text of names of the labels and predicting what is the most matching label of the text you provide. However, two important disadvantages of CLIP. One is it requires a lot of data. It was trained on like a huge amount of data, which even if it's noisy labeled and somehow parsed from the internet, still requires a lot of efforts. And the second problem is that basically it works on image level. It doesn't allow us some masks or some bounding boxes, some finer information than images. And those problems are basically somehow related. As we said earlier, if we have more dense predictions, such as masks prediction, we can use less data, less samples. And this brings us to referring image segmentation, which also uses both text and visual information, pictures, but in a different manner. In this way, in this task, we want to find the segmentation mask or bounding box in this picture from MDETR. Find the bounding box, a mask of the object, which is described with a text. In this case, this is pink elephant. This is a the picture contains an elephant which is painted pink. This is not a mask overlay. And MDETR in this case is able to detect this image and find its bounded box in the image by just using text supervision. So how they did it, this is very similar to DETR. This is why it's called MDETR. They use additional feature extractor, which in this case is Roberta, textual feature extractor, which extracts textual features. Those features are concatenated with visual features similar to DETR. And once again, this is passed through transformer. An important detail here that the labeling they used, as you can see from this picture, they used token-wise labels, which means for each word or couple of words, they labeled which object they refer here. For example, white pose here refers to pose of the cat, and all of them are labeled. So while this requires less data in a number of samples, this can be noisy. This should be requires relatively hard effort for labeling, because each of the objects referred in the sentence should be labeled and matched with corresponding token. So less data, but more effort for labeling, and still working with images. Which brings us to videos. Videos, on one side, people believe that videos are harder to work with, obviously requires more resources and stuff like that. But on the other hand, video often provide much more signal for training of the network. Similar, like segmentation provides us more signal than classification. In video, we have natural tracking, which often allows us to learn stuff even in self-supervised way. For example, tasks of object and instance segmentation, a pair of similar tasks. So object segmentation is basically tracking of the image of the object. You are given a label of a mask of an object in the first frame, and you need to track it across the video. And instance segmentation is more similar to image case. What would you expect from segmentation of instances? Just given the video, segment all the instances in the video. And this video shows from the paper named Dense Unsupervised Learning for Video Segmentation. It's NeurIPS 2021, recent one. And they did it in self-supervised manner, once again, using the fact that video has this temporal signal, which temporal correlations allows us to extract much more data from the images. So obviously, the same methods were tried with videos, the same methods we discussed about images. VisTR is adaptation of DETR to video case. It's relatively straightforward. So you just create the object queries you trained in DETR. You just duplicate them per frame. But the interesting part is that the same object query corresponds. So if you have, let's say, 10 object queries, the first object query should correspond to the same object in different frames. And this allows to perform tracking in a very simple way, as opposed to more classical methods. For example, you could do some kind of matching between masks in different frames based on their intersection to determine same object. Here, the matching is not needed. You can just use the particular object query to extract the masks over all the frames. And finally, this brings us to referring video object segmentation task, the task we were trying to solve. And I think you could already extrapolate from information I've given you what the task is. Given a video and the text query, you you want to predict a mask of the object described by the query in all the frames of the video, or sometimes not all the frames are required, because once again, even though you can extract more information from video, the labeling is more expensive. So some datasets label pretty sparsely, and some datasets are more dense. I'll get to it when I will talk about results. But in general, in benchmark, you won't need to predict for every frame, but rather for some subset, which we denote VI. And you can see an example to the right. So here is a dog, hand, and a yellow ball, 3 objects. And our goal is to detect that query refers to a hand, and then to find the mask of the hands. And this task is very complex, and it also inherently multimodal. It requires many different aspects in different modalities. First of all, text reasoning, as I said, understanding what query refers to, video understanding, instance segmentation, and tracking. And existing approaches typically rely on very sophisticated pipelines. I won't get here into details, first of all, because our approach is significantly different from others, so I'm not really an expert of other approaches. And second is we are outperforming every existing approach by such a large margin that I think that are less relevant now. So our approach is called multimodal tracking transformer, MTTR. So we are keeping with the naming of 4 capital letters ending in TR. And how have we done it? Let's start from a brief reminder of what transformers are. This is a scheme of a typical transformer network. So usually transformers use encoder-decoder architecture relying on self-attention mechanism. And I hope you remember what self-attention is. And in 2 words, it's approximate key value storage. Given a key, you get a value matching this key, but if you have a query which doesn't match key exactly, you get some approximate value. And if you have a sequence, we globally aggregate information from every other token. This is differently from, for example, convolutions, which use only local information. And it started for machine translation, but now it's basically everywhere. NLP is, I think, 99% transformers, and in Vision we have transformers now too. For example, DETR and VisTR I talked about, they use transformers for auxiliary task of detection, not for feature extraction, but also VIT and SWIN transformers, which are using it for feature extraction and images, show very promising results. And here an example of self-attention for in the text. You can see the lines connecting every 2 tokens, and the strength of the line shows how strong the attention is. And now I can talk about our method, MTTR. The key idea is to use a single multimodal transformer and model the referring video object segmentation as a sequence prediction problem. So we want, similar to VisTR, predict a set of instance sequences. And each instance sequence should attend a single object throughout the video. For example, it's a head, a ball, and a dog. And the additional task is to determine which instance sequence is relevant to our query. So, for example, in this case, the blue instance sequence is a hand, while a green circles is a dog, and we need both segment the hand and determine that it's the same objects over the frames, and decide that this blue square sequence is the referred one. And this is a pipeline. I know that this figure may look intimidating. It did for me at first, but I will go part by part and I'll explain every element, and you'll see that it's not that bad. But you can see 4 main stages here. I will give a high-level overview. We extract the features. We feed them to a multimodal transformer. We use it to predict instance sequence segmentation masks, and reference prediction head is used to determine the probability that the query refers to this particular sequence. And during training, we also do the instance sequence matching, which basically used to match the ground truth sequences to the predicted ones. So let's start from the feature extraction. Yeah. So we need a text and video feature extraction. Oops. Yeah, sorry. We need a text and video feature extraction, and it's done by, for video, we extract features from every frame, and we usually pass some window of T frames, which may be smaller than the full video, especially if the video is long. And we want the feature extractor to encode info regarding which instance appears, what actions they do. So we use spatiotemporal encoder, in particular VideoSWIN transformer. And VideoSWIN transformer is similar to swin transformer, but for videos, if you know what swin transformer does. If no, I'll try to briefly remind you. So the idea is to partition video frames into patches of pixels, and the patches are of different size depending on the depth of the layer. And the attention applied in local windows of patches. So instead of applying global attention between all the patches like we did, swin transformer applies only local attention. And as patch size increase, their number of patches decrease, and so the self-attention captures larger and larger context. In addition, they perform this shifting trick, which allows to also exchange information between different video windows. So just to be clear, swin transformers use videos to divide the video into subparts, and I'll also talk about different windows, which are windows of frames we used as an input. So usually when I refer to windows, I'm referring to windows of the frames and not the windows of swin transformer, which are less relevant. Those are internal details I won't touch. Okay, so for text feature extraction, we use transformer-based text encoder. We used Roberta base as our default choice, but other will work too. And those features extracted from text are duplicated TI times, and each relevant frame features are concatenated with text feature. So for each frame, we get a multimodal feature, which is a feature of this frame plus the same textual frame features for each frame. So as a result of feature extractor, we acquired a set of multimodal sequences, one per frame. And the second part is multimodal transformer. This is the part where the magic happens. So we have encoder and decoder layers, and those are shared weights transformers, meaning this is basically the same weights inputted by each one of the frames. So for encoder, we input multimodal features, and it outputs process features, which we are able to exchange information between the visual part and textual part. And this is important in the future when we use visual features for mask extraction. We want them to have the relevant textual features already. And in decoders, we feed the object queries, the same object queries from DETR and from VisTR, and encoded sequences from the encoder. So each object query queries a multimodal sequence to get entity-related information, and we hope them to each of the object queries to get the relevant object information, which is stored in the outputted object queries. So similarly to VisTR, as I already said, we have an instance sequence, which is object query in the different frames. And we want that this particular object query will attend the same object in different frames. In particular, if the object is absent from the frame, we would like to have an empty mask. So we would like the query to understand that the relevant object is outside of this particular frame, and to be able to output empty mask. And as I said, those are shared weights, so the same sequence has the same trainable weights across the frames. All this allows natural tracking of the instances, even if they are occluded or get in and out of the frame. So what's left is to generate predictions. So we input, I'll get back to the large picture maybe for a second. So first of all, we get the extracted multimodal features, and we extract just the visual part from them, but we also take the upper level features, which are outputs of the intermediate blocks of spin transformer. In our case, we used only 3 blocks, so the first and second blocks are passed as is, and the third block features are used as an output of multimodal transformer. So given all those features, we predict a sequence of segmentation masks and a sequence of reference predictions. Segmentation masks are just the masks. They should fit the corresponding object as good as possible. Reference predictions tell us 2 things. First is whether the object is the one that is referred, and whether it is present in the frame. So for example, the referred object is hand, so all other object queries are not referred, but also in first frame, there is no hand in the frame, so the first query is also not referred in this frame. And as you can see, the mask is empty. So how we do the sequence segmentation? This is standard FPN structure. As I said earlier, the visual part of encoder output sequence, which is extracted in multimodal transformer part, and outputs of the earlier blocks of temporal encoder. And this outputs the high resolution feature maps. So this is feature maps of quarters original input resolution. Those are the feature maps output by a special decoder. The segmentation kernel head, for each instance sequence, it generates conditional segmentation kernels. This is a well-known way to generate masks. Instead of predicting masks as an output of the spatial decoder, instead we generate some features and convolutional kernels. And then when we convolve the kernel with the feature, we get the output mask. This allows use a single set of features with multiple set of segmentation kernels to acquire any amount of masks. So the convolving the kernels with the feature maps produces a sequence of segmentation masks, one per frame and per object query. And we also perform upsampling to original resolution, obviously. The reference prediction head just predicts the probability that the corresponding object is referred by the textual query. And both of those heads fed the object queries. So the last part of the pipeline is sequence matching. And this is the regular bipartite matching, which is done with a Hungarian algorithm. The only interesting part is what is the weight of the edges, and this is defined by our losses. So matching cost function is built of dice coefficient and referring coefficient. So dice coefficient considers mask compatibility, meaning how good masks fit each other. And reference compatibility checks how good we are predicting that the object is referred. So our head is our prediction about whether the object is referred, where our I is ground truth. So we just do the inner product between two, and this gives us the weight of the edge. As a result, we match some instance sequence to the referred ground truth, and all the others are matched to some unreferred sequences. This brings us to optimization step, which is what are our losses. So remember that Y hat used to be the set of prediction sequences the previous step outputted. I'll abuse the notation a little bit, and I'll denote now by Y hat the set of the sequences permuted according to the optimal permutation, which means the sequences are now ordered in the order of ground truth sequences. So first sequence is the one which was matched to the first sequence. Second one is the one that was matched to second ground truth sequence, and so on. And we have two losses here. First one is the mask loss, and the second one is the referring loss. So for mask compatibility, we use the dice loss I've mentioned already, and also per pixel focal loss. For reference compatibility, we just use cross entropy loss of the referring logic. So this is a binary classification problem. Either the object is referred or not, and we perform a regular cross entropy training. During the inference, we drop this stop. We have no instances to match anymore. Instead, we just return the prediction sequence with a highest reference score. And the reference score is just the probability of being referred summed over all time steps. So I'll talk a bit about the results. We managed to outperform existing approaches by a large gap. So this table doesn't have all the latest approaches, but basically what happened in referring video object segmentation is that many methods were stuck at around 40 MAP. And our method was able to achieve 46.1 MAP with window size of 10 and with window size of 8, which is compatible to most of the previous works, we got 44.7, and we outperform most of the previous methods over all the metrics by a large gap. I think over any metric you'll find at least 5-7% gap. And also you could note that precision for large intersection over union, we have significantly boosted precision. For example, for 90%, we get like 7% improvement. This is shows that our masks are higher quality. And this was on A to D sentences, basically the default evaluation dataset. The second evaluation dataset is what's called JHMDB sentences. And here evaluation is performed without any fine tuning. So this checks generalization in some way. We use a pre-trained model on A to D sentences and evaluate it on JHMDB. One interesting detail is that in JHMDB, the masks are not labeled by humans, but rather they use some generic mask, which was matched to different instances. And that's why high precision, high intersection over union precision is very low across all the methods. Basically what happens is that ground truth mask is not really ground truth. Most of the algorithms are just performing better than this mask and unable to get higher than 90% IOU. And once again, here it's harder to see that the methods were basically stuck for some time, but we improved by 5% MAP and across all other metrics. But the problem with A to D sentences is that it's very sparsely labeled. Usually, I believe it has 3 or 5 labeled frames per video, which basically doesn't require any tracking. It just requires, you can extract temporal information, but you don't really need it to perform the predictions. And refer YouTube VOS is a dataset which came to solve this problem. It's a dataset based on YouTube VOS dataset, and in this case, the labeling is dense. It's every 5th frame is labeled, and they use a different metric. They use Jacquard similarity, which is IOU, but also F metric, which is some boundary related metric. And the funny story about this dataset is that they first published a validation set and training set, but then they unpublished the validation labels and turned it into a competition. Instead of validation test was turned into a test set, separated into public and private part. So public part is available for evaluation on the evaluation server. Private part is available only during the competition. So the upper part of the table is evaluated on the original validation set, while the bottom half is evaluated on a public validation, public set. So this result by Ding et al. This is a runner-up of previous competition. He got to the 2nd place. We didn't compare to the 1st place for the reason that they used large amount of pre-training data. And as I said, the video data is very hard to acquire. So the whole refer YouTube VOS is like, I think 4,000 videos. And being able to pre-train on additional data gives huge boosts. For example, VisTR we talked about in the beginning. they claim that pre-training on Coco gives like order of 10% boost in MAP metrics. So we are almost state of the art. If you are able to use ensembles and put a lot of additional data, you will be probably better than that. But obviously, any method would benefit from that. So we went for more or less fair comparison. As for ablation studies, first of all, we tried to check what is the effect of temporal backbone. So we could use some image backbone instead of VideoSWIN that wouldn't propagate any temporal information during the feature extraction, nor during the in multimodal transformer, which, as you remember, is per frame processing. So basically, this is using only static still image information, and we tried two different backbones. First is VideoSWIN T, but with window of 1, which means we just input a single frame of video to our feature extractor. And the second one is using DeepLab ResNet 101. This is the backbone used by previous state-of-the-art methods in PCI. And as you can see, even without temporal backbone, using just image information, we are able to outperform previous SOTA. Mind you that previous SOTA was around 40 MAP, and we get to 41 point something, depending on the backbone. So basically, even without temporal information, the multimodal transformers are so powerful that they're able to outperform any existing method. We also check more thoroughly what the input window size effect, and basically the larger is the window, the better you get. This is kind of obvious. The more information you get, the more you can extract it, but it's kind of starting to saturate around W equals 10. However, the additional advantage of using large windows, if you have enough GPU memory, is that the processing is faster. Since you can make predictions for all the 10 frames simultaneously, you significantly improve the speed of the processing. In particular, for window size of 10, we were able on RTX 3090 GPU to achieve, I think, around 70 FPS. Another thing we were trying to check is, does textual feature extractor matter? And it turns out not much. So for example, BERT outperformed Roberta by a bit, but I believe this is more or less noise. So basically, if your feature extractor is strong enough, you don't care how strong it is. And it makes sense because, first of all, the amount of different objects you see in the dataset is limited, and the sentences are relatively simple. So you don't need the GPT-3 to extract meaningful features. So now it's time of watching tons of fun videos. To be fair, when we were able to create this demo, which is able to process random YouTube videos, it took me like 2 or 3 days to just play with it enough. So I'll start from this video, which shows that we are able to detect a single object out of the crowd. This is, you can see a lot of people riding bicycles, and though there is a bit of the problem with the mask, which is glitching, it is able to detect this guy, which is have blue shirt as opposed to other people wearing different shirts. It's also able to use color as a supervision. So here there are 2 dogs, and the only difference between them is color. So white dog and brown and black dogs are both segmented right. I'll maybe explain that the color of the sentence in the upper part corresponds to the color of the mask. And so if you can see two queries here and two corresponding masks. So one idea we had that maybe we are able to generalize across languages. So I tried the same video, and at first I got very high quality masks. And I assumed that it is able to make good predictions even with a different language. But it turned out when I tried two queries, as you can see in this video, that basically the network is unable to process the text. So this is a limitation of text encoder. If you would use multilingual text encoder, we obviously would get it for free. During the training, the Roberta was frozen, or whatever textual encoder we used was frozen. So we could use, if we would use some encoder which is able to understand different languages, we would get the generalization. But in the interesting part here is that it's still able to produce very good masks. Masks are independent on the text part, more or less. So the features use this textual part in the multimodal transformer, but basically we are able to extract high quality masks independently on text query, and text query should in general only define the choice of the corresponding masks. Also, if you are interested, I forgot to mention that here in the bottom you can see the link to the video, which is exactly the same video. This is created using our collab. You're welcome to try to play with it. Another interesting question was whether we can generalize to unseen instances. And here you can see a wolf, which is segmented with a very high quality mask. And the network haven't seen any wolf in its training set. It obviously have seen dogs. So we get some kind of generalization, mainly because we use both pre-trained feature extractor, VideoSWIN, which have seen large amount of video. It's pre-trained on the kinetics data set, which is very large. And also similarly, Roberta is obviously familiar with the wolf concept, and that the wolf and the dog are similar things. So the only problem here is grounding. You only need for network to be able to communicate the concept they already recognize. And another thing, another sample of unseen instances. Here, a dog and a capybara. Obviously, no capybaras in training set. So this is a bit lesser quality masks. You can see that the network is confused, but it's still able to understand that capybara is not a dog. And each query, as you remember, is processed separately, so it couldn't use the information that the second instance is a dog for that. So it's just able to detect a capybara, even though it's relatively far, as opposed to wolf, which is relatively similar to dog. Capybara is, I think, very far from whatever they were in training set. And here is this is Love, Death, and Robots series. So this is basically a different domain. There are no multiplication in training set. It's mostly real life videos. Even though this video is relatively similar, it's not obvious that the network will be able to generalize to this new domain. Okay. And the network also understands directions. Here, for example, a dog and a cat, right and left. So the network is good in understanding right and left. And here is something funny happening. The network is so good at understanding the directions that the direction are basically the strongest prior. In a sense that I made a typo in a query, so I wrote the dog to the right, even though the dog is to the left. And it chose the entity to the right to be labeled with this mask. So it basically overfitted the directions because nobody gives the wrong direction. So if you give to the right, it doesn't care about what is to the right, just segmenting it as is. I'll get for a second to the questions. So yeah, the question is about checking different feature structures, tuning hyperparameters. We didn't work hard on tuning hyperparameters. We tried it a bit, but the first author is claiming that you can get a couple of MAP improvements if you work hard on tuning different hyperparameters and doing some simple improvements. So there are one of the problems of DETR, for example, I didn't mention, is that it's relatively slow converging, and there are multiple proposed solutions to how to improve convergence of DETR. So probably using one of those would improve the convergence of the whole network. So query engineering, or this is a thing I know, but I haven't tried it. I'm not that good at it. Different queries with a similar meaning work differently. And in particular, if you take a look on the training data set, it is very similar. It contains very similar queries built in a specific way. And using this specific way is usually improving the mask quality. Just, overfitting. That's what the network have seen. If you try different language, it probably will have some harder times, but then once again, we are using the generality of the feature extractor, hoping that it will work well. And actually the generalization is much better than we expected. I would never expect it to be able to segment capybara, for example. Okay, segmenting, as you can see, the segmenting foreground objects is simple. Sorry. So those masks, for example, are much better than the masks when I gave the directions. There is no, the capybara mask is, I think, almost perfect. So yeah, the queries matter. About the generalization, I think I'll talk about the problems I see in this particular task and in the evaluation protocols. I'll talk about it in a second. Long videos. To work with long videos, we split it into windows. You can technically, if you are very patient, you can run it on CPU. If you have enough RAM, you can run process the whole video in one run. This would significantly improve temporal consistency. You most likely won't have a mask which is inconsistent. Sometimes it will happen if the network is confused, but it won't jump from object to object. And obviously, it will allow better temporal understanding. So if you have an object which appears in the middle of the video, it will have hard times to segment it if the object is outside of the input part of the video. So for collab example, we are forced. So I don't pay for collab, so we have like K80 with 11 gigabytes of VRAM, and we limited the window size significantly, and it affects the temporal consistency. It barely affects the quality of the mask, but the temporal consistency is depending on the window size. Inference for different sequences. We do a full inference for each query. We tried to use multiple queries, but so for training, it didn't really improve anything, and it added additional complications, so we didn't do it. For inference, this is kind of outside of the benchmark, and once again, even though this is kind of most practical work I've done, we want people to use it, but we are limited by our benchmarks, and the benchmark wants the queries to be independent. Obviously, you can extract additional information if you use multiple queries during inference. So as for now, multiple queries are processed one by one. You can see it in the Colab code. Many objects of the same class. So you need to be able to refer to them. So I'll get back to the first example I've shown, which I believe is very impressive. So there are many objects here, many people riding the bicycles, and it's more or less segmenting the first guy. The problem is if you have like 500 instances or even 10 people, usually will have hard times referring to a single one. So if it's the one to the left, you'll be lucky and you'll be able to say the guy to the left, but it's mostly limited by your ability to refer to a single object out of the crowd with simple sentences. No, we use pre-trained feature extractors. Roberta is just frozen feature extractor. We didn't fine tune it, and VideoSWIN was pre-trained on kinetics. Technically, I think you could, if you have enough data, you don't need it, obviously, but the whole data set is like 4,000 videos. It's not enough. Obviously not for a language model to train, but also for visual feature extraction. If you had enough data, I think you need textual extraction, feature extractor to be pre-trained anyway, but visual feature extraction you probably could get away with. Self-distillation. I'm not sure. So one problem here is the network is eating a lot of memory, and it's not because it's large. We use the smallest possible visual VideoSWIN, the tiny version, and we use the Roberta base, which is not that large, and we trained it for YouTube VOS. We trained it, I think, on the A6000 GPUs with 48 gigabyte of memory, but you can do it maybe on RTX 3090 with 24, but it's eating a lot of memory, and not due to size of the network. I don't think you can reduce the size significantly. Also, the transformer, the multimodal transformer is it's only 3 layers, and it can possibly boost performance too. To be fair, we just didn't have time to experiment with it properly, but we only use three encoder layers, 3 decoder layers. So problems and future work. I think the main problem is low data amount. There is not enough data. If you want this to be general, if you want this to be practical, you need more data. The problems, which I think new benchmark, if they appear, should pay attention to, is larger time scales. So during training, we were able to process the whole video all the time. So we didn't have a problem of temporal consistency across different windows during the inference. So the videos are short in training set. And for practical applications, you probably would want longer videos. You know, so our collab is limited to 10 seconds, I think. And this is already a relatively large amount of windows, but you know, people, real life videos are long. I would love, minutes of videos, and it's a huge amount of frames. How you work with it, how you detect the actions, how you find the relevant objects in these large videos. So this is a problem which is not in any way not measured in current benchmarks. Temporal consistency, so it's measured in, it's not measured directly. So basically it's measured, obviously IOU will show you partially how consistent you are. You'll have low IOU if you're not consistent, but no direct measures of temporal consistency are provided. Generalization to unseen instances, as I said, it happens due to pre-training mainly, right? You have pre-trained feature extractor, both for text and videos, both have seen many objects in their previous training step. But the main problem now is for them to be able to communicate that the horse you've seen somewhere in the training set, or capybara, which you've seen somewhere in the training set, is the thing which is referred by word capybara. And Clip solves it by finding mutual embedding space. But this is, as we already said, both expensive. You can do it with 4,000 samples, whichever they are, and limited to this image-wide embeddings. So potentially, if you know how to solve the generalization problem, how to utilize the pre-training knowledge after we grounded it with small amount of samples, this could be huge. You could get very good generalization out of small amount of data for fine-tuning step. Do you think? Says the mask more programmatically instead of now turning them to text. I think this would be a separate problem. I think this is even existing problem, maybe not for videos, but for text definitely. Generally, the framework is top down, right? So I think you are able to, like, the mask output is good. You already have the masks, but you don't have if you would like to count the coins, you would like to detect the coins and then to understand that this is a thing you want to count. I think this is totally different task, but similar approaches probably can be used. I'm actually not sure what is a benchmark for this kind of stuff, but there should be one. Perceiver IO. Perceiver is cool, but it has, I don't think it would match as is. Like, you'd lose too much information or sequences would be too large, right? The idea in Perceiver is that you do some kind of projection in the beginning. You project it to some abstract space. If you have, I don't know, 3,000 frames of 600 by 300 pixels, this is huge amount of data. And for example, VIT, what they did, they project patches. They use learned projection, but it can be actually random because it is not losing information. It's high dimensional, but you can't possibly use sequences this large. And you need to somehow smartly extract the information out of these long videos. So Perceiver is cool for multimodal stuff, but I don't think it solves this long video problem. And super transformers for image segmentation. Yeah, Dino is cool. So there is a lot of cool works now. Dino is really cool. I was very excited when I've seen it, but it's not doing segmentation, right? It's not doing segmentation in the sense we are wanting we are wanting to do segmentation. Basically, does binary classification between foreground and background image, and it's also very coarse. Improving it to get real segmentation, even for images, it's not trivial task. There are some papers doing it. If you're following my channel, which you can see the link, you've seen probably some of those. But this is non-trivial task by itself. Do proper segmentation, for example, getting decent scores on Coco, it requires some additional stuff on top of Dino, which already is able to extract some information. Also, this one is cool. This is not by us. This is, you can see the Twitter link for the original posting. They use our network to segment the objects by textual description, and another network to do in painting. So basically, given the textual description of objects, you get them erased from the frame. And to be honest, it's a bit scary. It's literally a Black Mirror episode, but I think it's still cool. Thanks for listening. You can find contact information on my website. You can write me on Telegram. If you have any other questions, I'm reading the chat. There is a small delay, but I'm reading the chat. I will be happy to answer additional questions. Feel free to contact me if you are interested in our work. The work is fully open source. You can find the code, you can find the models, you can find the collab, you can use the Hugging Space, Hugging Face spaces if you're very, very, very patient. I think it takes like 10 minutes per input. But and I will be happy to collaborate if someone have any ideas to how to use our work or develop further. I don't think, yeah, the pin question is about strong zero-shot generalization. I think unfreezing Roberta is not a wise thing to do, because even though queries can be reached, there's still very limited form of language. It will probably lose a lot of generalization due to this, especially if you do long fine-tuning on large data. I think the more diverse data, maybe with lesser quality masks, maybe some kind of iterative noisy labeling could be useful, but the problem is this is very resource hungry problem. Yeah. Leave alone the fact that you need to label data, and in academia we don't do it, right? We just use the existing benchmarks. But also this would, so we are a small lab, okay, medium scale lab. So we were able to train those networks on relatively small amount of resources, no thousands of TPUs or something like that. Basically 2 servers, one with 4 A6000 and one with 8 3090. But trying to do it large scale clip style would require much more resources, both for training and for labeling. Thank you for listening once again. It was a very good experience, and I enjoyed the questions. They were inspiring, I think. And fortunately, I'm finishing for now my machine learning career, but I hope to see you sometime soon in some different events. Thanks. I think that's all.
Привет, я завершил трансляцию.